Hello, and welcome to our first video in the Linear Algebra series of videos. In this video, we will begin by solving a system of linear equations in multiple ways, and then we will use that as a springboard to look ahead to other things we'll be doing this term. So, all right, let's start. 3 ways of solving a system of linear equations. The first method we're going to look at is a method known as that of substitution. For the record, this was my favorite when I was in school. So, let's say I ask you to solve this system. First equation is x minus 4y equals 11, and our second equation is 5x plus 3y equals 9, and I say solve. Well, the first thing you should know is, what am I even asking you to do? I'm asking you to find values of x and y that make both of those equations true simultaneously. So, okay, what do we do in the method of substitution? Well, the first thing we do is we solve for a variable in one of the equations. Now I'm looking at the system, and you could choose any variable in any equation, but I look at the system and I say, oh, x in that first equation seems pretty easy to solve for. I'll choose that. So I do it, move the 4y or minus 4y over to the right, and so I've solved for x. I get x equals 4y plus 11. Good for me. Next step is I say, okay, now that I've got an expression for x, I'll substitute that expression for x into the other equation, and then I'll solve for the remaining variable. So what I mean by that is I take this expression, 4y plus 11, and I'll plug that in for x in the second equation, just like so. And now, all right, it's an algebra method to solve for y. I'll distribute that 5, so I'll get 20y plus 55 plus 3y equals 9. Then I will group the y's, so I get 23y. I'll subtract 55, so I should get 23y equals negative 46. And then divide through by 23 to get y equals negative 2. Woo! Okay, and we're mostly there. We've got our y, and now we can use that to find x. So we'll plug this value of y into one of the original equations, either one, and then just solve for x using arithmetic. So let's do that. Actually, let's cheat a little bit, and I'm going to plug y into this equation here because, all right, x has already been isolated. So do that. I get x is 4 times, now y is negative 2 plus 11 gives me x equals 3. There we go. Method of substitution in the bag. Like I said, my preferred method when I started learning this stuff. But all right. The next method we're going to look at is the geometric method, which I think is the most fun method, depending on your definition of fun and how boring your life is. So, all right, same system. Solve x minus 4y equals 11 and 5x plus 3y equals 9. And again, I want the value of a value of x and y that makes both of those true. Well, in the geometric way of thinking about things, we could say, all right, well, that first equation is the equation for a line, so let's graph it. Just graph the line, x minus 4y equals 11, and then graph the line that is the second equation, graph 5x plus 3y equals 9, and then any values of x and y that satisfy both equations, like the value of x and y that does that is the value where those lines intersect. So find the point of intersection. Now, all right, I obviously wasn't going to do this by hand. Life's too short, but I plug this into I think Desmos, and you get this equation was the line gives you the line x minus 4y equals 11. Here we have the line 5x plus 3y equals 9, and they intersect at the point x equals 3, y equals negative 2, which, thank goodness, that corresponds to what we got in the previous method. So I think I probably graphed these correctly. And then finally, we have what's known as the method of elimination. And in this method, what you do is you take multiples of the equations and then you add them to each other. And you do that with the hope of eliminating one of your variables. So let's go through and first say maybe eliminate x, and then we'll try solving for y. And so if I want to eliminate x, then I want to multiply this first equation, say, I think I want to multiply this first equation by -5. Because when I do that, I'll have a -5 coefficient on the x. And then when I add the equations, the x's will cancel. So, okay, if I'm eliminating x, in this scenario, I'll multiply equation 1 by -5, and I'm just going to add it to equation 2. So multiplying equation 1 by -5 gets me -5x plus 20y equals -55. And then, all right, let's add that to equation 2. And the x's cancel because, that's exactly why I multiplied what I did. And then we've got 20y plus 3y is 23y, and minus 55 plus 9 will be minus 46. And now, solve for y. Divide by 23, and we get y equals -2. And okay, like we did in the method of substitution, we could just take this value for y, plug it back into one of the equations, and solve for x. But since we're doing method of elimination, let's illustrate the method again by solving for y, or by eliminating y to solve for x. Okay, so if we're going to do that, now it's not quite so straightforward. Our goal will be, we're still taking multiples of the equations and adding, and now I want to eliminate y, so I want the coefficients of the y's, I want to multiply so that the coefficients of the y's are the same but opposite signs, like same number and absolute value but opposite signs. So I think I will multiply this first equation by 3 and the second equation by -4, and then add them together. So if I multiply this first equation by 3, I'll get 3x minus 12y equals 33. Oh, whoops. Yeah, that's just saying writing what I just said. So yes, okay, multiplying that first equation by 3, 3x minus 12y equals 33. And then multiplying this second equation by 4, I'll get 20x plus 12y equals 36. And add them together. Now the y's cancel because that's why I did it this way. And I'll have 23x equals 33 plus 36 is 69. Solve for x, divide by 23. Just, I think, an accident that I got that same number both times. And we have x equals 3. And good, this agrees with both of our previous methods. So, okay. Just reviewed a simple case of systems of equations. Let's use that to look ahead to what are we going to do for at least the beginning part of the semester. In this class, we are going to focus hard on the method of elimination. In fact, kiss the method of substitution goodbye. It was my favorite. Sorry if it was yours. We'll have to endure a little bit of heartbreak on this. We're not doing substitution anymore. We're doing only method of elimination. Why, you might ask? And the answer is, or one answer, is that the method of elimination turns out to be the best one suited for writing algorithms. And if you've ever had to solve a system where you have more than 2 equations and 2 unknowns, it is a giant pain. And in fact, you are begging for algorithms and you just want computers to do it for you. And in fact, it isn't what computers do. So we have written algorithms so that computers will solve these equations for us, and the algorithms that we have written use the method of elimination. And so we are going to see how those algorithms work, and we're going to see what computers do. And so that's why we're focusing on elimination. We're also going to think a lot about the geometric method. Like, we're not actually going to use it to solve systems, but we are going to think about it a lot. Why? Geez, just got a lot of questions today. Well, a main reason is that thinking geometrically generates insight. Okay, maybe you're not going to use the geometric method to find a solution, but you can think about what solutions are possible. Say in the 2x2 case that we looked at earlier. Say, well, all right, each equation represented a line, and so if the equations intersect, then we get one solution. Uh, if the equations are parallel, then we would get no solutions. And if the lines completely overlapped, then we would have an infinite number of equations, or sorry, an infinite number of solutions. So right away, thinking geometrically lets you know, I don't think you can have like 5 solutions. It seems like you can either have 0, 1, or infinity. So that's some geometric insight right there. Might be a real hassle to prove using just algebra, but geometrically, it's pretty clear. Another reason we're going to focus on the geometric method, at least we're going to think geometrically about these things, is that a lot of real world applications come down to geometry problems. And so if you are fluid in going back and forth between geometry and algebra, you can see a problem in the real world, see it geometrically, and then say, I know how to make a computer solve that for me. All right. The last thing I want to talk about is something that one might describe as a huge oversight in your book. Your book never defines what a linear equation is exactly. They kind of just assume you know, and maybe you do, but for the sake of completeness, I want to define it mathematically. So, mathematically, a linear equation is an equation that can be written in a certain form. It can be written like this. We've got this a sub 1 times x sub 1 plus a sub 2 times x sub 2 plus, all right, we're talking in general, all the way up to some a sub n times x sub n, and that equals b. And what are all these things? Like, what's going on here? Well, this x sub 1, x sub 2, all the way up to x sub n, those are our variables or our unknowns. And then this a sub 1, a sub 2, a sub n, and, all the a's in between, and this b, those are all numbers or constants. And equations written like this are called linear because, well, when you only have 2 unknowns, like x1 and x2, which we would normally just call x and y, when you only have 2 unknowns, the graph of that equation is a line. So that's why these are called linear equations. But I just want to note, what happens if there are more than 2 unknowns? Does your graph, and you graph that equation, do you still get a line? Yeah, no, never. Not anymore. If you have more than 2 unknowns, it's never giving you a line. So, for example, say we have 3 unknowns. 3x plus 5y minus 4z equals 3. Definitely satisfies our definition of a linear equation. We have our unknowns showing up, and there's numbers attached to them, and that equals a number. And if you might remember from vector calc, an equation like this, okay, you have 3 unknowns, so it's 3 dimensions. It's a plane. An equation gives you a plane in 3D, not a line. There are ways to describe lines in 3D with equations, but this is not it. And what if you had even more unknowns? Something like 2x1 plus 6x2, yada, 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 all of that equals pi. One of my favorite numbers, so I thought I'd throw that in there. What is that? Is that a line? Nope. That's actually a 4-dimensional hyperplane in 5-dimensional space, which is just, I think, cool. But yeah, super not a line. So then you might ask, okay, but is there actually something geometrically going on that's the same in all of these linear equations? Like, okay, they're not all lines, but are they all something else? Yes, actually. What all quote unquote linear equations have in common isn't that their graphs are lines, it's that their graphs are flat or straight. So, like, it's a straight line, it's a flat plane. And, okay, you might not have a great intuition of what, like, some 4-dimensional object in 5-dimensional space, what flat means for that, but there's a mathematical way of describing that. And linear equations are flat always. So actually, maybe they should have been called flat or straight equations instead of linear, but nobody asked me. All right, Thanks for tuning in. I'll see you in the next video.